for physical deployment, modeling supports virtual validation. So we need to simulate functional behavior using such as digital twins or hardware-in-the-loop setups, and BMS fault response to overvoltage, overcurrent, or thermal events, energy management system behavior under stochastic and generation conditions, and all of these pre-testing will reduce commissioning risks and ensures that the field deployment matches the designed operating envelope. So, and I would like to discuss about the operational readiness. So the models will help tune EMS and BMS parameters, forecasting daily SOC fluctuations, predictive maintenance by using state of health estimation, and how to prioritize the load and defer the load during load generation, which is actually really important when we are using the battery in rural African continent. And finally, the EMS and BMS configuration must be dynamic and field adaptive. So this will reduce remote reconfiguration based on usage pattern, derating functions based on ambient data, and also our academic contributions include developing open source co-simulation platforms where EMS, inverter, and battery models interact under real load curves, enabling better pre-deployment validation. And actually, I would like to discuss the last point, that we need to ensure proper deployment from day one. I'm thinking about the end of life, but of course, decommissioning activities. So when we want to invest on battery and install the battery, we need to think about the last day from the beginning. So that's why I brought these two tables to make sure that there are some parameters and steps that we need to take care from the day one. So how to estimate the end of life at some point from the beginning, not only if we have different use cases, so we will have different cyclings, so we will have different degradation from the battery. These are the points that we need to take care of that when we are selecting the application. And the decommissioning activities, so we need to think about those as well, because maybe in the next 10 years, 20 years, we need to think what we need to do with those batteries. Do we able to reinstall new batteries? How do we take care of that? So these are the main points that I would like to add actually at the latest. And yes. And just to conclude, battery energy storage system optimization in rural Africa is not just about hardware, it's about smart design, predictive modeling, and proper operational alignment. Through data, simulation, field engagement, we all can deploy actually batteries that last longer, cost less, and perform better, which we could say that our main goal is to reduce the levelized cost of energy by using the battery for people in Africa. Yeah, thank you.
Thank you so much, Zara, for your presentation. We will have questions for you by the end of Carl's presentation. In the meantime, Carl, whenever you're ready, you can start setting up your presentation on the screen. I would also like to remind everyone that I've seen some people saying hi in the chat, so please we encourage to get to know everyone and know a little bit about themselves. And also, if you have any questions, you also have the Q&A box. Perfect, Carl.
Okay, Christina, is my screen being shared?
Yes, it sure is.
Okay, great. Okay, thank you, Zara, for a very interesting presentation. My presentation is possibly going to be a bit more technical, but I guess that's because of the fact that we deploy these systems in the field. So here we go. So yeah, as already said, that if you look at electrifying the rural parts of Africa, the BESS systems will play a critical role. and the arguments for that has already actually been given. As we know that globally there are still quite a lot of people that do not have electricity, and there's almost 500 million of them in sub-Saharan Africa. And then there's a Mission 300 project that has been issued by the World Bank and some other partners to connect 300 million people in Africa to electricity by 2030. Now, if you do your sums, that's less than 5 years from now. And you all know that you do not build new power plants overnight. So the only way really is to go with renewable energy and associated storage. And as you can see on this picture on the bottom right, that's what sometimes is referred to as Africa being the dark continent. You can see at night there's a large part of Africa where the light, and that is in fact a metric being used to see where the opportunities are to electrify the rural parts of Africa. The other fact already mentioned is that renewable energy is intermittent. So you need a form of storage to help you provide with dispatchable power and stability. And then obviously storage technologies with renewable energy combined gives you the potential to provide access to these people rapidly and cost effectively. And I think that fits in nicely with the whole Repower project objectives. All right, and then, as I already mentioned, is that designing and operating a base in these isolated microgrids is no simple task. It's not overly complicated, but it's also not that simple because it is a mini power station. It's got to provide all the aspects of a proper power station, making sure that your system has reliable power. All right, so what are some of the challenges that you face in these isolated microgrids? So one thing which you can see in many reports is that there are difficulties in monitoring and maintenance. There is most likely a lack of skilled local technicians or capability. You obviously want to optimize efficiency so that you can maximize the energy yield. And you need to look at various operational strategies to avoid failures. For example, what happens if everybody in the community starts to acquire microwave ovens and they all use them at the same time, and then your batteries aren't big enough to store the power at night. So there are various strategies that needs to be looked at. Then you also want to try and maximize the battery lifespan to optimize costs over time. And then you want to be able to integrate with a diverse number of sources such as solar, diesel, and biofuel. I think in the Repower project, that's actually a big part of it, to look at alternative energy sources to just solar to try and create some diversity in power source. Then one other big challenge is operation in remote locations, as you can see on these pictures here, where we deployed a battery system to an island off Mozambique. Now, you can imagine the challenge of getting it there, as you can see. So you sit with major challenges in that aspect. And then another aspect that you've got to consider is temperature and other ambient climatic conditions, like humidity and salt and the heat and so forth, which all affect performance and lifespan. Like this system here, for example, sits near the coast, and you can imagine the effect of corrosion and so on that will have on the system if it's not properly taken care of. And then another point, but I think that's becoming something of the past, is the connectivity issues that can hinder remote monitoring and management. But I think that's something that can be brought under control quite soon. Right, so what aspects do we need to look at for considering a storage system for off-grid settings? So yeah, I think I'm going to repeat to a certain extent what Zara's already mentioned, but you want to look at cycle life. The more the better. Your BMS or battery management system quality is essential, and by that I don't refer only to the quality of the physical hardware, but also the software and the algorithms that is in that. So that's a very important part. Then lithium cells, I mean, these batteries consist of thousands of smaller cells, and they do tend to go out of balance if they're not being kept in balance. So therefore, part of your BMS is an important part is to have it balanced, and there you can look at active versus passive balancing. You need to look at the level of depth of discharge. So if you can discharge deeper without losing capacity, you have more available energy per cycle. Obviously, you want to look at reliability and durability, and you must be able to withstand these harsh conditions. And adding on to that is that if it's hotter, you get quicker degradation. So heat is an important consideration. You can see on that bottom right-hand picture there, we've got a battery in Namibia, and they've built a little canvas tent over it just to shield it from some of the sun to assist with keeping it cool. Obviously, the less maintenance you need, the better, especially for remote areas. We've got batteries in Zambia, and to get the technician out there can take up to 12 hours just to get there because of the remoteness and so forth. So yeah, you want to try and minimize maintenance requirements. And despite all of that, you must make sure that there is good after-sale service available. We find many battery suppliers that are a bit of a fly-by-night, and then when it comes to having service required, they can't supply that, and then that's not a good thing for the longevity of the project. All right, then suitability of the chemistry is obviously important, but I think nowadays lithium iron phosphate is so dominant in terms of all these aspects that the chemistry is almost not a factor anymore in a mini-grid environment. Okay, then energy density is important from a point of view that lighter versions are easier to transport, but they tend to be more expensive. So at the end of the day, I think lithium iron phosphate, again, is a very good compromise. Safety standards are important because you sit with high energy systems that are prone to potentially create disastrous fires, and therefore it's just important to make sure that the battery that you select has got appropriate safety standard compliance. And then like the life cycle cost, obviously, the cheaper that overall is, the better the payback on your investment. All right, so we've spoken briefly about the battery management system. And for those of you that are new to it, I'm just going to give a very quick overview of what it is. It's basically electronics and firmware that sits in the battery that measures the voltage of every cell, looks at the current and the temperatures of the cells, and then it estimates state of charge and state of health, and it controls contactors and charge and discharge limits, and it sets alarms and so forth if the battery is outside safe operating areas. And it also maintains usable capacity through balancing, which could be either active or passive. And why is this critical? First of all, it prevents overcharge and over discharge and thermal runaway, which is essential from a safety standards point of view. It also adds up to 40% of usable life cycle over the life of the battery, plus it underpins bankable warranties, which is essential from a financing point of view. And then it provides high-resolution data to the EMS that can optimize dispatch and report performance to investors. All right, and there's just a quick little indication of the difference between active and passive balancing. So this is a bit of a worst-case scenario, but let's say in this battery you've got cell 1 at 80%, cell 2 at 50%, and cell 3 at 40%. You can clearly see that if cell 3 gets to 0, the battery will technically be empty, but you still have 40% of capacity in cell 1, which you can't use. So what passive balancing does effectively, it gives you the average of the lowest cell in the pack. So that's not very efficient. You end up wasting energy in that balancing. Whereas with active balancing, you get the average capacity of the pack spread amongst all the cells if it works correctly, which means it results in more energy efficiency and higher yield on your investment. All right, then we've mentioned energy management systems before as well. So let's have a quick look at what they do and how they fit in with the BMS. That's the brain of the microgrid. And without that, you can't really have a microgrid functioning. So you need an EMS that can help you manage this. So it's not just optimal, it's vital for getting operations right in complex mini-grids. And it provides insights and control over the entire system, which means that they provide kind of a power station dashboard. As I mentioned before, a mini grid or microgrid is effectively a power station, and all power stations have these control rooms. The EMS gives us that capability to monitor and manage the system. And it also gives you the option to allow the transition to smart grids that can be operated and managed remotely. And BlueNova, so by the way, provides an EMS tailored for these complex off-grid scenarios. There you can see a number of functions that this smart energy management system can provide, which consists of categories of monitoring, analytics, system control, energy management, and then just notifications. I'm not going to drill into the detail of each of those. If you're interested, you can contact me afterwards. All right, so as we already saw, is that boosting efficiency and lifespan is important from an investment optimization point of view. And a good EMS-BMS combination will help boost that efficiency, where you can have intelligent charge and discharge cycles based on forecasts and loads. And you can minimize losses through power flow management. You can get a higher round-trip efficiency, which will increase your availability and reduces your cost. And that you can see that at the bottom, the simple difference between a 60% round-trip efficiency and a 98% round-trip efficiency is that for every 10 kilowatt hours that you charge into the system, on the one case you only have 6 kilowatt hours of usable energy, whereas the other one gives you 9.8 kilowatt hours difference, which is a massive benefit. So yes, the combination of an advanced EMS and BMS also helps you to make the batteries last longer. You get precise state of charge and state of health monitoring. And it's also very important to look at the thermal management and the cell balancing, especially in hot conditions. So ideally, you want to keep the average temperature of your cells at 26 degrees Celsius, and you want to minimize the difference in voltages between the cells throughout the battery. To keep in mind, this is specifically for LFP batteries. It's different for other chemistries, but with LFP being the main thing, that is typically what you want to achieve. And then you obviously don't want to prevent deep discharging and overcharging of these batteries, because that will accelerate degradation. And for those of you that still use lead acid, you will know if you discharge deeper than 50%, you accelerate the degradation quite rapidly. So yeah, then you just, this EMS-BMS combination allows you to look at sophisticated operational strategies that can optimize the efficiency and the life of the system. All right, then just a few notes on what the EMS can do from an operational strategy and failure avoidance point of view is that you need the EMS to implement these strategies to avoid failures. And using data analytics, we can identify potential issues in advance before they cause failures. You could see that one cell is falling behind and it's not being balanced properly. That indicates that there is definitely something wrong or something that can get wrong. So with this, we can actually identify these issues before they become a real problem. Then typically you also want to be able to look at fault detection and diagnostics to identify issues rapidly if and when that happens. You can see there at the bottom left, a typical dashboard of a mini grid where we've got 6 1 megawatt BESS systems, and this just gives you a dashboard view of the status, state of charge, temperatures, and so forth, which at a glance you can see everything is healthy or not. Then I think a very important part which have been experienced historically with mini grids or microgrids in Africa is the lack of remote monitoring and control. But nowadays it's becoming essential so that you can have expert intervention and management even in remote locations. I've popped a little Starlink antenna on there so that you can see nowadays it's actually quite feasible to have high quality 24/7 monitoring and management anywhere in the world. And it's not that expensive, and that could actually also be incorporated into some community internet access and so forth. So I think that all can become a very great win-win situation for everybody. The EMS can also take immediate action to protect the system in case of anomalies, and at the end of the day, ensure the stability and reliability of the power delivery, crucial for productive uses in these new areas. And then lastly, it gives you a unified platform for managing and monitoring all the components like PV generators, batteries, flywheels, whatever else you might have on the grid. So yeah, in summary, what would I consider to be the key takeaways? BESS are essential for a stable, reliable power situation in rural microgrids. And specific expertise and technologies, and that the EMS is crucial for overcoming many of those challenges, and that a good EMS and BESS combination will help boost your efficiency and make your batteries last longer, and it enables operational strategies to avoid failures and make sure that facilities are managed appropriately. So yeah, the careful selection, deployment, commissioning, integrations are vital, and you want to optimize the cost of the system under the specific operating conditions. And then obviously the long-term support capability is essential. So when you do look at BESS suppliers and partners, make sure that they have the ability to give you long-term support, at least 10 years, if it's not more than 10 years. And then choose a partner like BlueNova that can help you with integrating the systems with the EMS and so forth. You can see in the top right there is one of our mini grids in South Africa. It's not a completely off-grid system, but it can provide off-grid power to an estate of over 6,000 households. It contains 6 1 megawatt by 2.5 megawatt hour batteries. And with that, we can actually form the grid and provide power to a fairly large community. All right, and then there's just a snapshot of a few of the installations that we've got. You can see there's a system in Mozambique with a generator which provides power to a rural community. And then we've got a number of installations on game lodges and so forth, and a few more commercial installations that provides power stability and backup to those clients. And then, yeah, just lastly, a little bit of information on BlueNova. We like to believe that we are a partner in energy storage, especially from an African point of view. We've got installations in over 10 countries. We produce a fairly large amount of storage. We've been in operation for, I think, going for 10 years now, with operations in Firgrove near Cape Town. And we've got a technical support center and warehouse in Centurion near Johannesburg. And then from a repower project point of view, we are providing 928 kilowatt hours worth of storage to the various installations. I'm not delving into detail there, but effectively it's for 8 storage units. And we are introducing our BMS systems and so forth with these. And the first battery system has been shipped off to, I believe, AGT, Africa Green Tech in Germany, which will then be evaluated there. And I think Zara and the guys will work on those. And we're also getting ready to ship some batteries to some of the destinations in Africa. So yeah, I think with that, that's my story. Thank you very much.
Thank you, Carl. Okay. All right. Well, thank you so much, Carl, for that presentation and have that on-field experience shared with us. So we're going to move on to the discussion, and we have a couple of questions from the audience. So we're going to start with those. If anyone has more questions, feel free to write them down. So in the chat, in the Q&A chat box. So let's start with the first one. Zara, Carl, any of you are welcome to answer. I'm going to start the first one with Carl, maybe because you've already had any of these issues happening to your projects. But how do you think the impact of considerations of factors like willingness to pay of users, income, and other factors on battery sizing and selection happen? And how can you optimize it?
Yeah, no, that's a difficult question. Because that deals with with one of the key success factors to these projects, and that is the funding and financing of these projects. And obviously, if you can get end users to pay for it, then it makes the viability of the project much more sustainable. And also you'll find that if people pay for something, then they take care of it and they respect it. Whereas if it's given to them for free, you get all sorts of potential abuses coming through there. Yeah, so I don't really have too much to add from a financial point of view there, because this is typically what the project developers would take care of. And all I can say is that some of the functionality in the EMS includes the possibility to create bills or billing systems. So if you add meters to the consumers and you can have an accurate record of consumption patterns, one can create bills which would allow you to get revenue from the end users. But yeah, I don't know. I can't really say much more than that.
Perfect. Zara, is there anything you would like to add?
Yeah, sure. Actually, that's a good question, because it depends on at which stage you're looking into. For example, if you're at the planning stage, that you're doing the sizing of different components and specifically battery for your consumers or your microgrid. But I would say that maybe one of the main, keys that we can take care is that for the first stage, what we're looking at is the peak consumption of whatever the community, for example, that we want to develop the microgrid there. But there are some strategies like demand side managements that can, because we all know that the batteries are the most costly, actually, or the most expensive components in the microgrid setup. So whatever we can do in reducing the size of the battery, so we can save for levelized cost of energy that people needs to pay actually in the future. So what we can do is that we can size based on the peak consumption at the beginning, but then by some sort of load shifting, demand side management, whatever is related to managing the load, so we can reduce the size of the battery at that point. So we can have some, I would say, consideration on the income of families as well. But what I can say right now is mostly related to the demand. How do we manage actually the demand or the consumer side? Yeah.
Perfect. Well, thank you so much. Next question comes from Marvin. Do you see a role for batteries in industrial applications in Africa? Zara, let's start with you.
Okay, I think maybe Carl knows better because he's working in the field. But what I can say from the academic point of view, yes, of course, because as I said in my presentation, industrial consumers are, we can assume that these are the productive users. So that's why we need to, take care of those loads as the main, not the main load, but the loads that will actually introduce more capacity, or if we need more capacity from the battery side in the microgrid installation. So yes, of course, but we need to take care of, again, how we manage that kind of loads, if we can run them during during non-peak hours, but of course, this is something that would be interesting, actually. to use batteries, of course, because of the power outages and everything else.
Great. Well, thank you, Zara, for your academic point of view. Carl, do you have anything to add?
Yeah, look, most of you might be aware that we've been having grid supply issues in South Africa for the last couple of years, and electricity is like a drug. Once you've got it, you're not very happy when you don't have it. And the only way you can really ensure the reliability of and quality of power is by having battery backup systems. And that's one of the main market areas for us in South Africa at the moment. But then again, having traveled through Africa at various sort of stages in various countries, power outages are quite common across Africa, even for the people with grid support. And also the recent drought in Zimbabwe and Zambia was another great example where the people in Zambia didn't have power for like 20 hours a day. Now, so in an environment where you already have grid access, a battery system will give you continued supply and running. I can tell you from experience, running a PV system with battery storage is way cheaper than having to run diesel generators. The economies just make absolute sense. And yeah, we've got several industrial applications where we've got batteries running. For example, we've got batteries running at a sawmill in Malawi, a big industrial site and so forth. So no, I think as electricity availability spreads, I think the combination of mini grids and microgrids supporting the grid will become more and more common across Africa.
Perfect. Well, thank you, Carl, for that answer. I'm going to take with me your quote of electricity is like a drug, because I completely agree. Zara, you had another one of BESS is not a backup, but a backbone. So incredible phrases for today. So next question. It's going to be about tariffs. So Carl, let's send you this one first. Rural mini-grids tariffs tend to be higher than those of National Grid. What do you think are the average % increase to tariff from the addition of BESS, if there's any?
Yeah, it's an interesting question. If you've got a reliable utility that supplies you with constant, reliable power from the grid, then yes, you can say that in many cases, for now, the grid is cheaper than what it would cost to put up your own plant. But the moment you start those generators when the grid goes off, the equations change, and it doesn't take a lot of outages to get the BESS system to pay for itself. And if you are in an off-grid environment, you don't have an alternative. So then the tariff actually doesn't make any difference. It's cheaper to run a combination of renewable energy with storage. And if the grid is reliable, obviously, then the finances don't make sense. But in South Africa, in some places, depending on where you are, it kind of already makes sense to actually have a mini grid supported power supply as opposed to relying only on the grid. So yeah, it's a complicated question with complicated answers depending on the context of the situation.
So it is. There's not a one sole answer, definitely.
No.
Okay, Zara, would you like to add anything, or shall we pass to the next question?
No, I think Carl covered most of the points.
Okay, the next one. This is an interesting one too. What opportunities exist for collaboration with training and research institutions in Africa as a means for growing local capacity in BESS? So I don't know, Zara, if you have any experiences that you can share with us.
Yeah, I think maybe as we are working on Repower project, and we do have some collaborations on different activities. So maybe I would ask you actually to guide us on this as a part of maybe work package, and how do we manage the collaboration. But of course, we would be happy actually to collaborate on different topics on battery energy storage systems. But from the regulations and everything else I need to check. Yeah.
Definitely. There is opportunity. I think there is space for collaboration. Just depends a little bit what you're looking for and the different targets and objectives. I'm going to put the link to our Repower project again, so if anyone wants to take a look at it, and also our email, because of course there's always room to get to know more in this space. Carl, do you have anything that you would like to add, or should we pass to the next question?
Now, look, if you look at the plan to put electricity onto 300 million people in 4 or 5 years, there are two main constraints to that. The one is financing and funding, and the other one is capability and capacity. Now, the World Bank is doing great work with various partners to make funding available, but you cannot do these projects without capacity and capability. So yes, I think this is a very important point that needs aggressive attention. And I think that it's also an amazing opportunity for job creation in Africa, because one can train up sufficient skill to do the installations and the monitoring and the maintenance. So I'm very excited about this. I see this as a massive opportunity. But yeah, it will take fairly significant coordination between various parties, governments, universities, and yeah, we'll see what we can do to help that. Fortunately, it's not too complicated. I think with good training programs, one can establish capacity and skill within a couple of months. It's not that difficult. It's not a nuclear power plant. It's actually relatively simple to put together.
Okay, next question. So we talked a lot about the battery lifespan and how to take care of it. But what are the environmental considerations for battery use and storage? And can the batteries be recycled after they have been degraded? What's the second life of these batteries? Zara, I'm seeing you nod. Would you like to answer this question?
Maybe I can talk a little bit about the recyclability for, the end of life. Of course, whatever we are doing related to the smart EMS and BMS, those factors will be really important during the first life of the battery itself. How do we operate them? Whatever we can do during the operation will increase or decrease the lifetime of the battery, of course. But from the end of life, which I would say we can say when the state of health of the battery will go down, less than 80%, I would say. So we can say that the lifetime of the battery is done at some point. But right now, what I can see, it is still under the research development for the recyclability. That's why I mentioned in one of the slides that we need to take care of decommissioning at the beginning as well. So because this is not something still doable at some point from the battery part. Yeah.
Perfect. Thank you. Carl, do you would like to add anything, or should we pass on to the next question?
I see the time is starting to run out, so let's move on.
Okay. All right. We have a very long question from Adiso, but I'm going to shorten it up because I see that the question's at the end. What does it take for investors, companies, and researchers to develop high-capacity, long life with smart BMS and EMS battery technologies? Carl, let's go with you.
Okay. So I think that the technologies are basically quite mature and available, and there's so much progress being done that I don't think there's really much room for developing technologies at the moment in competition with the rest of the world. I think the more important thing is to get the capacity on the ground to be able to install and operate and manage these systems. The innovation in applications will come once you've got a certain basic track of penetration into the environment. It doesn't stop companies from doing, or universities from doing research and development, because I'm sure there will be African-specific aspects that needs to be looked at. But that ship has sailed, and it's sailing fast. You look at the EV revolution that's coming across the world. That's creating such an economy of scale that the technology is just falling in our laps. So I think that one's taken care of.
Thank you so much. So shall we move to the last question, or Zara, would you like to add something else?
No, I think we can move on to the next, yeah.
Okay, all right. So the final question is, in BESS, how does the energy losses during charging and discharging affect the efficiency of the system? Zara, would you like to?
Yeah, sure. I can say a few words. Actually, in battery energy storage system, in general, energy will be lost during both charging and discharging, and we know that because of the internal resistance and also power electronics. So this will reduce the round trip efficiency. So I would say there are some considerations that should be taken into account for that internal resistance, and also the selection of power electronics when we want to connect our batteries to the inverter part. This is my actual idea.
Okay, perfect. Thank you. Carl, would you like to add something else?
Well, I think I did cover it to a certain extent in my presentation, in that round trip efficiency is important, and the higher it is, the better, because then you've got less losses. And losses are also not nice in that it heats things up, and then you've got to get rid of the heat, and then that increases losses again, because now you've got to run cooling and fans and so on. So high energy efficiencies are good. And today I think we're quite close to optimal. Modern day inverters are very efficient, and lithium iron phosphate batteries are also very efficient, especially if you charge and discharge them at relatively slow rates. Then the internal resistance losses are relatively low, and you can get efficiencies above 92%, which is actually very good considering other forms of energy provision.
Thank you. So we have a couple of minutes, so let's finish up with a couple of other questions that we have. So some questions that come up is, how do you decide on the size of the battery? What considerations do you take into account? Carl, would you like to answer this question?
It's again one of those questions which can take an hour or two to answer.
We have 4 minutes.
Yeah. So first of all, you need to see what would be the average and the peak demands from the clients. The peak demand determines the size of the inverter that you want, and the average demand determines the energy storage that you require. But often that does not really tie up with the available funding. So at the end of the day, it's a compromise between what is wanted and what can be afforded. And then you'll find a midway between the two that gives you the answer. And I can't give you a magic formula that gives you a perfect answer. There's always a fair amount of engineering and optimization that goes into such an exercise.
Perfect. Well, thank you. Zara, would you like to add something to Carl's answer?
Yeah, I just wanted to mention that it's a kind of optimization, or it is obvious from the name, optimize, actually. So it's a matter of we need to have a trade-off between, but of course, the peak demand will play a key role, actually, if we want to have 100% reliable power, for sure, yeah.
Perfect. Okay. I think we have time for one more question. Let me see. It's from Wei. It says, can we have an outlook for the development of BESS innovation in the near future? Which could be interesting, of how do you see the development of BESS, how it will develop in the coming years. So Carl, would you like to answer this question?
If you look at the industry evolution of PV, for example, over the past 10 years, we've seen significant drops in cost and significant uptake in deployment. And until about 2 years ago, lithium iron phosphate technology was still relatively expensive, slowing down its penetration, but we've seen major sort of drops in cost over the last few years. And I think the general belief is that that cost drop will continue to the point where it again becomes very affordable, and then we'll see massive take up in the environment on that, which in turn again with the EV revolution will result in reduced cost and increased efficiencies. I do not foresee any major chemistry breakthrough in the medium term. I mean, sodium batteries are coming out, but they still cannot compete with lithium iron phosphate at this stage, and the developments in lithium iron phosphate is just so dramatic because of the volumes that are sort of turning out. So all I can say from an innovation point of view is that the main thing is that the cost will keep on coming down, quality will keep on going up, and that will just result in a huge, I think, surge in demand.
Carl, thank you so much. Zara, would you like to add anything to?
Yeah, maybe I just want to say one sentence. Based on the learning in Europe, what I can see, actually, the most important thing is to find a longer lifetime of the battery. For example, as we can see, LFP batteries are, if we look at the cycles, they are totally different from the previous chemistry, and also the second life batteries, which are coming from EVs. These are some developing stages for batteries, at least what I could see.
Perfect. Well, Zara, Carl, much for your time today and answering all these questions from the audience. Also, thank you for coming to all the participants today and asking these questions and kind of have this discussion. Just a reminder, we will send the link to the recording and the materials available in a couple of days. We will be also having more webinars from the Repower project. So please stay tuned, and we hope to see you very, very soon in one of our other webinars. So thank you so much and have a great day.
Thank you. Bye-bye.
Thank you. Bye.